Light from TON 618 began its journey more than 10 billion years ago, at a time when the universe itself was still learning how to form galaxies. Long before Earth existed. Long before our own galaxy took its final shape. That ancient light carries more than energy. It carries a record of violence, growth, and gravity on a scale the modern universe no longer produces. Hidden inside that glow is a black hole with a mass of 66 billion suns. A gravitational engine so vast that entire solar systems could disappear inside it without ever touching the edges. According to everything we know about physics, about black hole growth, about the limits of cosmic time. An object like this should not exist so early in the history of the universe. And yet, TON 618 is real. Its light is real. Its mass is real. And its existence quietly challenges the foundations of modern cosmology. So tonight, we ask a dangerous question. What if the universe learned how to grow its monsters long before physics was ready to explain them? To understand why TON 618 should not exist, we first need to understand what it actually is. TON 618 is not a star, and it is not a galaxy. What we observe is something far more extreme. It is a quasar, one of the most luminous objects ever discovered, located near the boundary between the constellations Canes, Venatici and Coma Berenices. When astronomers first recorded it in the 1950s, it appeared as nothing more than a faint blue point of light. Only later did spectroscopy reveal its true identity. This was not a star at all, but the blazing core of a distant galaxy powered by a black hole of unimaginable scale. A quasar forms when a supermassive black hole enters a phase of intense feeding. Vast clouds of gas and dust spiral inward, accelerating to relativistic speeds as they fall into a rotating accretion disk. Friction and compression heat this disk to extreme temperatures, causing it to radiate across the entire electromagnetic spectrum. Radio waves, visible light, ultraviolet, X-rays, and gamma rays all pour into space, transforming the galaxy's core into a beacon visible across billions of light years. The black hole itself remains dark, but everything around it burns with extraordinary brilliance. What makes TON 618 exceptional is not only that it is a quasar, but when it existed, the light we see today left its source more than 10.8 billion years ago, when the universe was less than a quarter of its current age. Galaxies were still assembling their structures. Stars were forming in chaotic bursts, and cosmic order was far from settled. TON 618 allows us to look directly into that violent era, offering a rare glimpse of how the first massive structures evolved. In this sense, TON 618 is more than a distant object. It functions as a time machine embedded in light. Every photon carries information about conditions that no longer exist. By studying its spectrum, astronomers can reconstruct the chemistry, density, and motion of matter from the early universe. Few objects offer such a direct connection between present observation and ancient cosmic history. If TON 618 is a time machine written in light, What secrets is it still hiding about the universe's earliest and most violent chapter? At the heart of TON 618 lies a black hole whose scale defies everyday intuition. Current estimates place its mass at roughly 66 billion times the mass of the Sun, classifying it as an ultramassive black hole. This is not simply a larger version of the supermassive black holes found in most galaxies. It belongs to a category so extreme that only a handful of known objects even approach its scale, and none match it in both mass and luminosity combined. To grasp what this means, consider its event horizon, the boundary beyond which light itself can no longer escape. For TON 618, this boundary has a Schwarzschild radius of roughly 1,300 astronomical units. In physical terms, that corresponds to nearly 390 billion kilometers across. Our entire solar system, from the orbit of Mercury to far beyond Pluto, could disappear inside this sphere of darkness with room to spare. And this is only the size of the horizon, not the region of space where gravity already dominates everything around it. The comparison becomes even more striking when we look closer to home. Sagittarius A star, the black hole at the center of the Milky Way, weighs about 4 million solar masses. TON 618 outweighs it by more than 15,000 times. If Sagittarius A star is a gravitational giant, then TON 618 is something closer to a cosmic god. Its gravitational influence reshapes space and time on scales that challenge the limits of our physical models. This immense mass also affects how matter behaves nearby. Gas clouds do not simply orbit and fall inward. They are stretched, compressed, and heated under extreme tidal forces long before reaching the event horizon. Time itself slows dramatically in these regions. From afar, an object approaching the black hole would appear to freeze, its final moments stretched across centuries. Scale, in this environment, is not just about size. It is about how deeply reality itself is distorted. TON 618 forces us to confront a profound problem. Objects of this mass require enormous amounts of matter and time to form. Yet the universe had barely begun assembling galaxies when this black hole already existed at full scale. Its size is not merely impressive, it is unsettling. What kind of environment could possibly feed and grow a black hole of this magnitude in the young universe? TON 618 is not merely massive, it is violently alive. At its peak, it ranks among the most hyperluminous quasars ever observed, radiating energy equivalent to hundreds of trillions of suns combined. This level of brightness is so extreme that the quasar outshines its entire host galaxy, erasing the stars around it from view and announcing its presence across the observable universe. Yet, the source of this light is often misunderstood. The black hole itself emits nothing. It is perfectly dark. The brilliance comes from the accretion disk that surrounds it, a vast rotating structure of gas and dust pulled inward by gravity. As matter spirals closer, orbital speeds rise to a significant fraction of the speed of light. Friction, compression, and magnetic turbulence heat the disk to extraordinary temperatures, transforming gravitational energy into radiation with astonishing efficiency. Inside this disk, particles collide at extreme velocities. Electrons are accelerated. Ions are torn apart. And magnetic field lines twist and snap. These processes generate radiation across the entire electromagnetic spectrum. Radio waves trace the outer regions. Visible and ultraviolet light dominate the blazing core. Closer still, where gravity and temperature peak. The disk unleashes X-rays and gamma rays powerful enough to ionize matter across intergalactic space. TON 618 does not simply shine. It floods the universe with energy. This output places the system near the theoretical limits of how efficiently a black hole can convert infalling matter into light. In physical terms, TON 618 operates close to the Eddington limit, the balance point where outward radiation pressure nearly equals inward gravitational pull. Push beyond this boundary, and the quasar would begin to choke itself, blowing material away faster than it can consume it. The fact that TON 618 remains so luminous suggests an environment of extraordinary density, order, and supply. In this state, the quasar becomes more than an object. It becomes a process. Matter is consumed. Energy is released. Space is ionized. And the surrounding galaxy is reshaped. The light we observe is not decoration. It is the visible signature of gravity operating at its most extreme and efficient. If TON 618 shines brighter than the galaxy that hosts it, what does that reveal about the environment feeding and sustaining such overwhelming power? TON 618 is not merely massive, it is violently alive. At its peak, it ranks among the most hyperluminous quasars ever observed, radiating energy equivalent to hundreds of trillions of suns combined. This level of brightness is so extreme that the quasar outshines its entire host galaxy, erasing the stars around it from view and announcing its presence across the observable universe. Yet, the source of this light is often misunderstood. The black hole itself emits nothing. It is perfectly dark. The brilliance comes from the accretion disk that surrounds it, a vast rotating structure of gas and dust pulled inward by gravity. As matter spirals closer, orbital speeds rise to a significant fraction of the speed of light. Friction, compression, and magnetic turbulence heat the disk to extraordinary temperatures, transforming gravitational energy into radiation with astonishing efficiency. Inside this disk, particles collide at extreme velocities. Electrons are accelerated. Ions are torn apart. And magnetic field lines twist and snap. These processes generate radiation across the entire electromagnetic spectrum. Radio waves trace the outer regions. Visible and ultraviolet light dominate the blazing core. Closer still, where gravity and temperature peak. The disk unleashes X-rays and gamma rays, powerful enough to ionize matter across intergalactic space. TON 618 does not simply shine, it floods the universe with energy. This output places the system near the theoretical limits of how efficiently a black hole can convert infalling matter into light. In physical terms, TON 618 operates close to the Eddington limit, the balance point where outward radiation pressure nearly equals inward gravitational pull. Push beyond this boundary, and the quasar would begin to choke itself, blowing material away faster than it can consume it. The fact that TON 618 remains so luminous suggests an environment of extraordinary density, order, and supply. In this state, the quasar becomes more than an object. It becomes a process. Matter is consumed. Energy is released. Space is ionized. And the surrounding galaxy is reshaped. The light we observe is not decoration. It is the visible signature of gravity operating at its most extreme and efficient. If TON 618 shines brighter than the galaxy that hosts it, what does that reveal about the environment feeding and sustaining such overwhelming power? The existence of TON 618 presents one of the most unsettling problems in modern astrophysics. We are not simply dealing with a large black hole, but with one that reached an extraordinary mass at a time when the universe itself was still young. The light we observe today left TON 618 when cosmic structures were only beginning to assemble. According to conventional timelines, there should not have been enough time for a black hole to grow this large. Standard growth models rely on gradual processes. A black hole forms from the collapse of a massive star or a dense gas core, then increases its mass by steadily accreting surrounding matter, even under ideal conditions. With continuous feeding near the theoretical maximum rate, this process takes billions of years to produce a supermassive black hole. To reach tens of billions of solar masses so early would require an almost uninterrupted and perfectly efficient growth history, something the chaotic early universe should not easily allow. TON 618 forces scientists to consider more extreme possibilities. One scenario suggests that it began not as a small seed, but as an already massive object formed through the direct collapse of enormous primordial gas clouds. In this case, the black hole would skip the slow stellar stage entirely, emerging at birth with millions or even billions of solar masses. Another possibility is that early cosmic environments were far denser and more orderly than previously believed, allowing black holes to feed at rates far beyond what we observe today. There is also the question of mergers. In the crowded young universe, collisions between proto-galaxies and their central black holes may have been far more common. Repeated mergers could rapidly boost mass, accelerating growth beyond standard expectations. Yet even this explanation struggles to account for the sheer scale of TON 618 without pushing existing models to their limits. What makes this challenge so profound is that it is not an isolated case. TON 618 stands as the most extreme example, but it belongs to a growing population of early massive quasars that collectively strain our understanding of cosmic evolution. Each one suggests that the universe may have learned how to build its giants far faster than our equations predict. TON 618 is not simply a data point, it is a warning. Somewhere in our theories of gravity, matter, and time, an assumption may be incomplete. If TON 618 did not grow the way we expect, are all ultramassive black holes following a path we have yet to discover? TON 618 is not only defined by what falls into it, but by what it violently throws back into the universe. Like many powerful quasars, it is capable of launching enormous relativistic jets. Narrow beams of plasma accelerated to speeds approaching the speed of light. These jets erupt from regions near the black hole's poles, and can extend for millions of light years, far beyond the boundaries of the host galaxy itself. The origin of these jets lies in the interaction between gravity and magnetic fields, as matter spirals inward through the accretion disk. Magnetic field lines become twisted, compressed, and amplified. Near the black hole, these fields act like cosmic railguns, channeling charged particles into tightly focused streams and flinging them outward with immense energy. What escapes is not ordinary gas, but superheated plasma moving at relativistic speeds, carrying enormous momentum across intergalactic space. These plasma outflows are far more than visual spectacles. As they plow through surrounding gas, they heat, ionize, and displace matter on vast scales. Entire regions of the host galaxy can be stripped of cold gas, the raw material required to form new stars. In other regions, shock waves triggered by the jets may compress gas clouds, briefly igniting bursts of star formation before exhausting the supply. The jets act as both destroyers and sculptors, reshaping the cosmic environment over millions of years. The physics governing these processes is extreme. Temperatures soar. Particle densities fluctuate violently, and magnetic reconnection events release sudden bursts of energy. In these regimes, plasma behavior becomes highly nonlinear. Classical models of fluid dynamics begin to break down, and even modern plasma physics struggles to capture the full complexity. Observations suggest that some jet features may involve particle acceleration mechanisms that remain poorly understood, pushing the limits of standard theory. In systems like TON 618, jets represent a critical form of feedback. They regulate how fast the black hole can grow, control how gas circulates within the galaxy, and influence the long-term fate of surrounding cosmic structures. The quasar does not simply consume its environment, it actively engineers it, sending waves of energy far beyond its immediate reach. If these relativistic plasma jets can reshape matter across millions of light years, how deeply can they alter the future evolution of the galaxy that gave birth to them? The light from TON 618 is more than a signal. It is a messenger that has crossed billions of years of cosmic history to reach us. As it travels through intergalactic space, this light does not move through emptiness. It passes through vast clouds of diffused gas, traces of matter left behind as the universe expanded and evolved. Each encounter subtly alters the light, encoding information about regions that are otherwise invisible. By analyzing the spectrum of TON 618, astronomers can study how this ancient light was absorbed, scattered, and redshifted along its journey. Specific absorption lines reveal the presence of ionized hydrogen, helium, and heavier elements in intergalactic space. These signatures allow scientists to reconstruct the chemical composition of the universe at different stages in its early development, long before galaxies like the Milky Way had fully formed. This technique turns TON 618 into a powerful cosmic probe. Its extreme brightness ensures that its light remains detectable even after traveling across immense distances. Unlike faint galaxies that fade into noise, a hyperluminous quasar provides a clear, continuous background against which the structure of the early universe can be mapped. From this data, astronomers can trace how matter clustered, how filaments of the cosmic web emerged, and how the first large-scale structures took shape. TON 618 also offers insight into the epoch when the universe transitioned from darkness to transparency. During this period, intense radiation from early stars and quasars gradually ionized neutral gas, allowing light to travel freely for the first time. Observations of quasars like TON 618 help constrain when and how this transformation occurred, refining our understanding of one of the most critical phases in cosmic history. In this role, TON 618 transcends its reputation as a gravitational monster. It becomes a guide. Its light acts as a timeline, linking present-day observation to conditions that existed shortly after the Big Bang. Through it, we do not merely observe the past, we measure it. If the light from TON 618 carries records from the universe's earliest eras, what hidden clues might it still reveal about the moments just after the Big Bang? For all its enormity and brilliance, TON 618 is not the final word. Astronomers have identified other black holes that may rival or even exceed its mass. Objects like Phoenix A that push the upper boundaries even further. Each new contender reminds us that TON 618 is not an anomaly isolated in darkness, but part of a population of cosmic giants whose full distribution we have only begun to glimpse. At these scales, certainty becomes elusive. Measuring the mass of a black hole across billions of light years relies on indirect methods, spectral lines, luminosity models, and assumptions about how matter behaves under extreme gravity. Small uncertainties can grow large, yet this uncertainty does not weaken the discovery. It strengthens it, because even with conservative estimates, TON 618 remains far beyond what our comfortable theories were designed to explain. This is where TON 618 becomes more than an object of study. It becomes a boundary marker. It tells us where our models still work and where they begin to fracture. Our equations describe how black holes grow, how galaxies evolve, how energy and matter interact across cosmic time. But TON 618 sits at the edge of those descriptions, quietly insisting that something is missing, or incomplete, or misunderstood. Science advances not when answers are confirmed, but when questions refuse to go away, TON 618 forces astrophysics to confront its blind spots. Did black holes form faster in the early universe than we believe? Are there growth mechanisms we have yet to observe? Or is our picture of cosmic history itself still unfinished? In this sense, TON 618 is not a failure of science. It is an invitation to revise assumptions, to build better instruments, and to ask bolder questions. The universe is not obligated to match our expectations. It reveals itself on its own terms, one extreme object at a time, and as TON 618 slowly fades deeper into cosmic time, its message remains clear. The universe is larger, older, and more capable of surprise than we ever imagined. If TON 618 already challenges the limits of modern science, how much more will the next discovery force us to rethink what we truly know?